Okay, everyone, welcome back to the Masters in Bioethics here at St. Thomas University. And we're beginning the morning. Benesha, welcome. We're beginning the course on environmental bioethics, human population, and environmental bioethics. Always beginning with a little prayer. In the name of the Father, the Son, and the Holy Spirit. O Lord, send forth your Spirit, and we shall be recreated. You shall renew the face of the earth. Amen. All right, so the first thing I want to do is some brief introductions. First of all, various folks are coming in at different times, either online or in person, because of previous committees, commitments. And then some have to leave early, so there'll be a flow in and out of class today. But I also want to welcome 4 new students to the program and to this course. So we have Denisha Sparks, who is here in person. And then we have Kendall Brock and Sarah Desheen and Kenneth Desheen online. Kenneth is actually going to see the video because he's coaching a football game this morning. And different people have commitments. That's why I also record the lectures, as you know, and then make a YouTube out of it so that there's no excuse for missing the lecture. And that's what's important, whether you see it in person or virtually or later, but there is no excuse. And for the benefit of the new students, the way we work it out is by summaries, right? So you notice that a couple of days before Saturday, I normally send you an email with the PowerPoint for that lecture and also an outline and the Zoom link, right? So I'm projecting here the outline that you can see and you can use for the summary. Now, the assessment for each course, as you know, is making a summary of the lecture between 2 to 4 pages, 2 better than 4, but it's up to you, really. A summary is not the whole lecture, but the highlights of it. So here is a summary, here is an outline of today's lecture. And some students actually open this up since it's a PowerPoint, it's active. You can open it up and start typing in your summary as I go along, as I'm lecturing. So by the end of the lecture, some students already have their summary done, at least in draft. And then you can always clean it up a little bit, make it a little tighter, and then email it to me, right? And that summary is due by Wednesday midnight. Wednesday midnight is the due date for the summary of each lecture. What I do then on Thursday morning, I download all those summaries and go over them and make my notes on the piece of paper and give it a grade, which is on a scale over 100%, right? And then by next Saturday, I have that summary already corrected for you and give it back to you for feedback. And that's how we work it. And the grade for the course will be the average of all the summaries. At the end, I take the average of all the summaries, and that's your grade. And typically students do well, but of course, it all starts with making a good summary, right? And the reason for that is that when we summarize things, we need to reflect on them and we need to crunch them, as it were, tightly into significant, informative sentences and even bullet points, if you will. But the important thing is that I can see on the summary that you have understood the lecture or not. So before going forward, any questions or comments from the new students or from the old students, just old by being in the program before, all right? Okay, so you know, as teachers, we always talk, and unless someone asks a question or a comment, we just keep on talking, all right? And I'm a consummate teacher, so if you have any question or comment or anything at all during the lecture, just jump in and make your statement. Otherwise, I just keep going. All right, so I do pause periodically a little bit to see if anyone wants to say anything. All right, so hearing none, then I'm going to dim the lights here for the optimal thing. Let me see, that one needs to go off and this one, yeah. All right, so we have natural lighting for taking notes, and we also have a little darkness in the room for the PowerPoint. So you can see okay, you're welcome to sit anywhere within the room. Connect online, and we go forward. All right. Again, this course is Human Population and Environmental Bioethics, which is the complement for human life bioethics. And you notice since I'm merging two cohorts here, cohort number 6, and you folks are halfway, hopefully by May. Cohort number 6, the 7 of you will be graduating already. All right, so you have 2 more semesters. But cohort number 7, which is starting now, you have 4 semesters ahead. So by May of next year, in other words, by the end of this academic year, you will be halfway through the program. And there will be summer and fall of 2023. So you will be graduating in December. God willing, okay? And that's how we work it. So for the benefit of the new students, I'm also going to do just a very brief review. The program as such, I say that today, contemporary bioethics has 2 main pillars or 2 broad topics that have to do, on the one hand, with human bioethics. Human bioethics, you can think of beginning of life issues, end of life issues, healthcare issues, right? Those are all bioethical topics with regards to human life. And then there's also the environment. So environmental bioethics is the other pillar or the other broad range of topics that have some bioethical implication today, right? So for the old cohort, we have covered already human bioethics, at least beginning of life and end of life. You'll have next semester in the spring, you'll have healthcare bioethics, all right, which will be like the 3 subtopics of human bioethics. But for the new cohort, you're starting with environmental, and then we'll move on to beginning of life and end of life and healthcare in the next semesters. Okay. Now, with regards to human population and environmental bioethics, again, as you know, my style is, so bioethics is a compound word that has both biology and ethics. And in principle, by themselves, they would have nothing to do with each other because biology is one of the empirical sciences, meaning that things that can be measured, and biology studies life, right? I'm talking about organic life here on Earth, not the life of the saints or the life of the Blessed Trinity or angels, but rather organic life as we know it here on planet Earth, right? And the only organic life that we know so far, including our own. And that's biology is a study of life on Earth, whereas ethics is one of the disciplines, one of the branches of philosophy, which has to do with human behavior, ethical behavior. In other words, what's right or what's wrong according to the dictate of conscience. And therefore, because it's philosophy, it's not empirical in the sense that it can be measured with an instrument, in contrast to life, nature, which we can measure. We can measure the weight, the size, the amount of radiation that the organism is giving off, even metabolic processes down to the molecular level and so forth. all that can be measured, right, with actual instruments. Whereas in philosophy, we don't have a physical mechanical instrument to measure human thought and reasoning or behavior, but we do have a philosophical instrument, which is reasoning. In other words, the brain actually becomes the instrument of philosophy by analyzing, right? Critical thinking is really the instrument of philosophy and ethics. Christina, welcome. Come on in. All right. And therefore, it's a complement. You know, we have the physical and the metaphysical. Physical meaning anything that is material, and we talk about mass energy equivalence today. And metaphysical is that which is beyond the physical, but is nonetheless real. The fact that an item, a thing, is metaphysical doesn't mean that it's just fantasy or that it doesn't exist. It does exist, it's very real. In fact, it's a deeper aspect of reality than the physical reality. For example, the existence of God, the Blessed Trinity, and even the realities beyond life and death, essentially eternity, they are realities that are actually deeper than the reality that we're living here today. All right, but it takes critical thinking to get there. And that's why the good Lord has given us a mind to use. So it's not just the brain, the organic organ, let's say, but actually the thinking that occurs upon that brain, which is what we call the mind or the thought process. And so there's complementarity going on here, which again, in the sciences we call elegant, how the metaphysical complements and really makes sense out of the physical, right? Because otherwise, when we consider, for example, death, our own death, what's the point in all this suffering if it's all going to end up rotten in the grave, right? Well, the metaphysical gives us an opportunity to give sense to our life, to give meaning. And so the metaphysical questions are, who are we? Where did we come from? Where are we going precisely after death? And in the little insight about that, which we covered last semester with the beginning of life, when the fundamental principles in bioethics, is why is it that humans have been burying their dead since the beginning of the human species, even with clothing and food inside the grave? So we can see, we can intuit, we can glean that there is a belief in the afterlife of some sort, even in the most primitive humans that have ever existed, before any of the technology that we see around us today, right? So that those are insights for the mind to then ponder and reflect. All right, back to environmental bioethics, which has to do with this planet. What we're going to do then is lay out first the physical. In this case, we'll see a little bit more biological in the second half of today's lecture, but the first half is going to be more physical and somewhat chemical, right? Realities with regards to the origin of the universe and the origin of the solar system and the origin of Earth, and then the origin of life, actually, the origin of life we covered in the fundamental principles of bioethics. But we'll stop there in the second half of the lecture. Okay, so an overview for the whole course. We have 7 to 8 modules. There may be an 8th module here that I'm cooking in my mind because we still have about 13 weeks ahead of us in this semester. We're using the full fall semester for this particular course. And so we still have about 13 weeks ahead, and it's a module per week. So we have room even to fit an 8th module here, which would be contemporary things, because in the issue of climate change and global warming and loss of biodiversity, a lot has happened even since the last year, which was the last time that I taught this course. So I may have an 8th module there to update us on stuff that is happening right now, becoming even more dramatic with regards to the environment that surrounds us, the nature that surrounds us, okay? But as always, you know that the last lecture, there's never a summary for it. So it's basically just soaking it in and pondering. But for the 7 modules that we have established for this program, for this course, we'll look at the different layers of Earth as we see them, as we observe them. So again, to understand the physical reality of a planet and the chemical reality of our planet, and then finally the biological reality of our planet, okay, which lives on the crust, only the crust, which is the thin outer layer of our planet. Kind of even the peel of an orange would be too thick to compare it to the crust of the Earth, where life occurs. All right, so we have today's lecture on the geosphere, basically the actual physical formation of our planet, all right, beginning with the Big Bang, and we'll accelerate through that. The next lecture is going to be on the atmosphere, meaning the gases that form the layer that covers the Earth, and it's actually a shield, it's a protective layer, mostly against radiation and other stuff that is coming from space. Then finally, the hydrosphere, because this planet is the only one that we know so far that has liquid water. Liquid water is very significant because when we're thinking about life, again, organic life, we know that the basis of life on Earth is liquid water, because essentially at the chemical level, it's a bunch of chemical reactions in an orderly fashion, what we call metabolism, that gives for the possibility of life, all right? And so having liquid water on Earth is key for life as we know it. Then we're going to go into cycles, which is the dynamic interaction of these 3 layers of the Earth. Then we're going to look at energy flow through the system of the Earth. And then we'll look at human population in regards to our existence, again, here on the planet that holds our life. And finally, we'll get into the topics of climate change and loss of biodiversity and so forth, the current crisis, if you will, of the environment, of the ecosystem. So those are the 7 weeks that we have ahead of us. There'll be a couple of Saturdays where there will be no lecture, for example, the Thanksgiving weekend. And also, I think it's in a couple of Saturdays. Let's see, let me pull up that date so that you have it ahead of time. In October, right? Not Columbus Day, rather October 1st, because I have another Rescate prison ministry on Saturdays, all right? So in a couple of lectures, actually we have in 3 lectures time, the first Saturday of October 1st, there will be no lecture because I'll be away. But then October 8th, we'll pick up again with module 4 and continue on down, all right? And then the next break is going to be precisely in Thanksgiving. All right, continuing. So this is an overview of the entire course. Moving forward then, we're going to look at, in today's lecture, very briefly, a recap of the origin of the universe and the origin of Earth. That has to do with cosmology. Then we'll get into geophysics and the theory and the fact of plate tectonics and continental drift on the crust of the Earth. where we have actual life occurring. And then in the second half of the lecture, we'll get into the biomes, which are the big pictures of ecological systems, the food web and the food pyramid. In other words, the dynamic interaction between living organisms. And then finally, various classifications going beyond the species. We have populations, communities, ecosystems, biomes, and finally, what we call the biosphere, the whole living planet. Okay. Now, we have to do a little basic physics here and some basic terminology for physics and the matter-energy equivalence. So I'm going to pick up on Einstein and his great contribution of the mass-energy equivalency. Or the mass-energy equivalence, right? Which is the famous formula of E = mc squared. We can use this one. Capital E equals lowercase m, lowercase c squared. Now, capital E stands for energy, any kind of energy. Who can give me one type of energy? One type of energy. All right, kinetic with respect to movement or no movement, right? Kinetic energy is what? Energy in motion. In contrast to kinetic energy, what's the other category? Those are two categories of energy. It's not what I was looking for, but we'll take it apart. What is the other category of kinetic energy?
Potential.
Potential, right? Exactly. When an object is not moving, an object has potential energy. So for example, this water bottle on top of the desk has potential energy and no kinetic energy, but it has potential energy. Very interesting. Now it has, I'm moving the bottle to the edge of the desk. So now it's receiving some kinetic energy from my finger, right? From my movements, which means that some of my potential energy is being wasted in the kinetic energy of moving the thing. Negligible, but it's using some ATPs, right? Some energy source for my body, my muscles moving that bottle. As I move the bottle closer to the edge, we'll get a little more anxious, right? Because there's water inside the bottle. And, but the bottle is still fully 100% potential energy. If I keep pushing it, which I will not, that potential energy will turn into kinetic energy, right? It will spill over the edge and hit the carpet, and it will hopefully will not go beyond the carpet, right? It will stay at the carpet and rest, right? So what is the potential energy that this bottle has? It's in relation to what? The fall itself, yes. So it's a force that is invisible, but we can measure it. It's a force that the bottle is experiencing. And I can tell you, I'll give you another hint, it's a force of attraction toward where?
It's towards the ground.
Exactly, it's toward the ground.
Gravity.
Beyond the ground is to the center of the earth, and we call it gravity. We could have called it chamum, you know, we could have called it anything else, but we call it gravity. All right. So that was Newton's elegant discovery and quantification, actually, of gravity to give us a formula to give us it's a type of acceleration. So when this bottle falls to the ground, right, the pull is a gravitational pull. Someone has a mic on. Sorry, check your mics, please. Thanks. All right, so there is a gravitational pull, and it is an acceleration. In other words, it's not just a velocity. Sorry, somebody has the mic on. Hello? If you don't mute yourself, I will mute you. Father Franco.
Yes, Father.
Okay, your mic was on, so I have muted your mic. All right. You can still unmute it if you want to talk to us only. All right. So gravitational force, which is one of the 4 fundamental forces in nature, right, is an acceleration. It's a force of attraction. And it's not just a constant speed. For example, if we get on the Palmetto Expressway or 995 and we reach 55 miles an hour and we're going to abide by the law and we push the button on the speed control, whatever that's called, cruise control, right? Cruise means constant speed. The car should stay at 55 miles an hour. All right, should stay at 55 miles. So that's a constant speed. It's not an acceleration. An acceleration is accelerating up to 55, or if I disable the cruise control and don't touch any of the pedals, the car will start decelerating, right? Which is a negative acceleration. It's an acceleration in the negative. In other words, it's not a constant speed anymore. It's losing speed. Why is the car losing speed? Correct. But why is it that the car doesn't continue by inertia at 55? What is
gravity?
Yes, but there's a filter in between the gravity. Physically, immediately, what is the point of contact? I'll give you hints. What is the point of contact between the car and the road?
So it's mass on friction.
Yes, the 4. Exactly, the 4 tires, right? The 4 tires are touching the road. Yes, so is the road moving with the car? No. The road is fixed, but the car is moving, right? So you have 2 different motions there, if you will. The road is moving in relation to the Earth rotating around the sun, but not in relation to the system of the Earth itself. And the car is moving, but like Jose said, on that system of car and road, there is a force, which is a force of attraction, which is gravity. And what is gravity doing to the road? Yes. Is gravity affecting the road? Yes, by way of potential energy. The gravity is pulling on the road down, but the road is already fixed to the ground, right?
I guess the gravity makes sure that we don't go to air unless we're driving the car.
Correct.
We are just making sure
That we don't fly away.
Right.
That's correct. But so the gravity is acting on the road and it's also acting on the car. In which direction?
Opposite.
Downward. Opposite to what?
No.
Downward, right? The car is moving like a tangent on a circle. The tangent is a straight line on a circle on the periphery of the circle, right? And that's the movement of the car, but the gravity keeps pulling down, and so the car stays on the road and doesn't fly away, like Christina says. But what is happening is that because the tires are moving through the road, the tires are moving, but the road is fixed. So there is friction, right? There is friction occurring between the tire, and there's that expression where the tire meets the road, right? That's the point of friction. So where the tire meets the road is the point of friction. If we were able to get in between, if all of a sudden we become microscopic and we have a microscopic lens in our hands and we get in between the tire and the road without being squished, we would see that there would be, what would be happening to the tire? There will be molecules of rubber flying off the tire, molecules of rubber flying off the tire because of the friction. Because the road at the macroscopic level is acting like sandpaper. There'll be some molecules flying off the asphalt also, some molecules of tar. And that's why a new road looks black. But an old road looks gray, light gray, because the old road has lost tar and the old tire has lost rubber because of the friction. So there's a sanding going on, and that's why periodically every 3 or 4 years we have to change the tires because of friction. Okay, that friction slows down the car because the force of gravity is pulling perpendicular to the motion of the car, right? Perpendicular, which is 90 degrees. And it will always be 90 degrees as that car is circulating around the earth. That's a circumference, right? So these are the physics, and don't get tired yet because we're just getting started with the mental gymnastics here. We're still just on E. All right. Just to point out that there is, okay, thank you, because that brings us back to reality. There is kinetic energy and potential energy, right, as the two large categories of energy. All energy, all types of energy, they be classified. Better move this guy back in just in case. All types of energy can be classified into potential energy and kinetic energy. And there is also an equivalency there, a back and forth between kinetic and potential energy, right? However, the types of energy, different types of energy, just that, like there's different type of matter. What's the simplest matter that is stable? I'll give you a hint. It's on the wall, it's represented on the wall there by that chart. What is that chart called? The periodic chart of the elements. So again, then the words are meaning, and especially nouns and verbs and adjectives in science have a lot of meaning. So element is the noun in that phrase, right? Periodic table of the elements. Elements, there's a periodic table. The simplest element is what? Hydrogen, because it has how many protons? 1. And the next simplest element is He, helium, exactly, because it has how many protons? 2. And so on down the line. So you see that the number above, has the number in red is the number of protons in the nucleus. The number in black below is the atomic mass. And we talk about the difference between mass and weight, which is very important because the scales don't lie, but we lie when we read our mass and interpret it as weight. All right, we'll get there. So basically, the basic stable unit of matter generically is the atom. But there are different types of atoms. The elements. So we can put quality into the different types of atoms, right? The elements. And we go from the simplest elements to the heaviest elements with literally 100 protons in the nucleus. Right, so the basic unit of matter is the elements, the various elements, and all matter is made up of atoms, therefore of elements in various combinations. Okay. But also for energy, there are different types of energy. And what is one type of energy, for example? The difference between day and night. When it's night and we go into a room, we flip the switch. What kind of energy? Light energy, all right? Well, oxygen is oxygen energy. The combustion that oxygen produces, cellular respiration, releases energy, but oxygen is an element, and therefore is matter. There is energy in food. What kind of energy? Of the two categories, kinetic or potential?
Oh, I will say it's potential.
Exactly. And specifically, what type? Where is it mechanically, chemically? Where is that energy, that potential energy stored?
Stored
In the chemical bonds, specifically between the carbons, carbohydrate. When we burn the carbs, when we burn the carbohydrates, so it's chemical energy. Potential energy is chemical energy, different from light energy, which is photons, different from electrical energy, which is electrons flowing, right? So you got photons, you got electrons, you got chemical bonds. Those all have energy, potential or kinetic, whether it's moving or not, right? So different types of energy. Another type of energy that the sun gives off, for example, in addition to light energy. Hot or cold?
I mean, it's like, how do you call it?
Hot or cold, the sun? Hot or cold? I mean, so heat is another type of energy. Can we measure heat? What do we use for measuring heat? Thermometer. So you see, energy can be measured. Energy is not metaphysical. Energy is not fantasy. Energy is not a figment of my imagination or a pigment in my imagination, that some kid used to say. Energy is real. If I put my finger into that socket, I know that energy is real because I get electrocuted. All right. So that's energy on the left of the equation. And the equation itself is significant because it means equal. It means exactly, not even approximately, it means exactly equal, as opposed to unequal. All right. Mass times c, which is the speed of light. It's also known as the universal constant, and that's why c, lowercase c, very humble, lowercase c, you know, is the fastest thing in the universe, which is the speed of light. All right. And it's a constant. It's not an acceleration. So far, the fastest thing that we have discovered in the universe is a photon, the speed of light. And m is mass. So before we get to c, as we go from wonderment to wonderment here, let's pause on mass or matter for a moment. Because this is known as the mass energy equivalency. You know, essentially that energy is equal to mass multiplied by a constant, or if we solve for mass, C is multiplying on this side. If we pass it to the other side of the equation, what does it do? It divides. So energy divided by C squared will give us mass. All right. Most of us have not grasped the implications of this equation, but I'm going to take you there in a minute. Okay, so what is mass? Does this have mass? The water bottle. It has mass, all right? It's got plastic and it's got water. So those two, a solid and a liquid together, make up the total mass. So I weigh this on the scale. And let's say it gives me half a pound. All right. And so that's the British system. We can either use metric or British. In science, we use metric system because it's universal. British system is British and it's non-decimal, but the metric system is decimal. Anyway, so I measure this, and let's say that for the sake of a scale that we're accustomed to, right? Because we all know our weight more or less, and what we actually weigh and what we would like to weigh and all that. So we weigh ourselves on the scale. But the scale doesn't really give us our weight. The scale gives us our mass. So I'm saying that the mass of this bottle with its water is half a pound. That's not the weight. That's the mass, which is this guy, this M. All right, that's M for mass. The weight is mass times what? Not volume, it's a force. So weight is mass times a force. And what is the force that is pulling on this bottle as it sits on top of the scale? What is the force that is pulling on our body as we stand on top of the scale?
Gravity.
We can be dressed as in a winter with 3 coats on top of us, you know, in winter, or we could be stark naked, but there's a weight on top of the scale, and there's a mass on top of the scale. The mass is our body, with or without clothing. The weight is mass times gravity. Okay? And so weight doesn't have the scale, the units of kilos or grams or pounds. The weight is in joules, all right? Which is mass times gravity. And so gravity is the Newtonian constant, which is 9.8 meters per second, right? 9.8 meters per second squared. That was, oh, that's the acceleration, sorry. Oh, okay, so the movie, I don't want the movie physics. The movie was kind of like that. A lot of science fiction in the movie. All right. Looking for. Okay. 9.8 meters per second square. Per second. All right. That's, yes, that's the force of gravity. So you see why it's an acceleration? It's per second square. So 9.8 meters. How much is a meter? Okay, here I have my hand meter, which is about a yard, which is about 3 feet, more or less. All right, so 3 feet is a yard, and it's about a meter. We're translating from metric to British. So it's the length of one arm and the chest, or the other arm and the chest. It doesn't matter which arm and the chest. More or less, both arms are more or less the same length, right? So an arm and the chest, more or less, is a meter. So 9.8, let's round it up to 10. 10 meters per second square. All right, 10 meters per second square. So if I drop this bottle to the ground, you know, let's say 1 meter, if I drop it 1 meter, by the time it hits the ground, it has accelerated to 10 meters per second square. All right. If I drop it from 2 meters, by the time it hits the ground, it would be 2 times 10. So it will be, by the time it hits the ground, it would be 20 meters per second square, and so on. And it doubles every, so it's an acceleration. Okay. Right, so 10. Therefore, let's say when I weigh myself, I weigh 150 pounds, right? 150 pounds. Is that my mass or my weight? You know where I'm going. That's my mass because it's in pounds. All right.
Okay.
So the scale doesn't lie, but the scale gives us our mass, not our weight. Why? Because the scale is also subject to the same gravitational pull as the body that's on top of the scale. But the scale gives us the mass. If we want to know our real weight without lying, we would take our mass, which is what our scale gives us, which is 150 pounds, times 10. Times 10. Well, those are the units, yes. Those are the units. So my mass is 150, but my weight is 1,500. Yes. Well, it will be pounds per meter per second square. All right. And that's the real weight. So the scale doesn't lie, but we lie. We take off one whole unit. When we say, well, I weigh 150, I don't weigh 150, I weigh 1,500. I mass 150. Because pounds or kilos or grams is a measure of mass, not of weight. If I want the weight of a thing, I have to multiply it times gravity, which also means that I weigh less on Earth than in space. Because if I'm away from the gravitational pull, I weigh less, but I mass the same. My mass is constant. Unless I eat when I'm in space, then I'll weigh, my mass will be my personal mass plus the mass of what I ate. All right. But my mass remains constant in space, but my weight varies with regards to the gravitational pull. And in space, I'm not only subject to the gravitational pull on Earth, but I'm also subject to the gravitational pull of the sun, just like the Earth is. And on Earth, I am subject to the gravitational pull of Earth and the gravitational pull of the moon, the sun also, and the sun and the moon and the other planets. So there are many forces, and all those forces are moving. Well, there's one force, which is gravity, but the source of gravity is moving around at different times of the day and night and the year, because sometimes the moon is here, sometimes the moon is not here. Sometimes the sun is here and sometimes the sun is not here. But the Earth is always here. So the one constant gravity on my body, our bodies, and on everybody's body on the Earth is the Earth gravity. But then there are all these other gravities that affect a much lesser amount, but they're there. Okay. And if they weren't, we would feel it. We would feel it. Basically, we would feel generally heavier because it will only be gravity pulling. Because the other forces, either way, the other gravities are pulling out of Earth, right? They're not at the center of the Earth. They're outside. They're on the periphery, so they're pulling out. Gravitational pull of the moon makes me literally lighter on Earth when the moon is above. And heavier when the moon is not above. Because it's counter, it's pulling, it's the same gravity, but it's pulling against the Earth gravity. All right, back to MC squared, right? So we understand energy. We have a basic concept of energy, rather. We have basic concept of mass. Now C, I mentioned is the gravitational, it's a constant. It's not an acceleration. Only when it's squared does it, that becomes an acceleration. But by itself, C is a constant. That's why we use C. And it is the universal constant, which is the speed of light. In other words, the fastest thing that we have been able to measure empirically is the speed of light. Specifically, the speed of a photon, which is a unit of light. Just like an atom is a unit of matter, a photon is a unit of light. An electron is a unit of electricity, right? Now, let's think of a photon and the speed of a photon, the speed of light, okay? Here it is in meters per second. You notice second is not squared as such because this is a constant speed. In the formula, it's squared, but not C by itself. C by itself is a constant. The seconds are not squared here. So it's a constant speed, right? 299,000. Let's round this up again to 300,000. Okay? 300, well, okay, it's given it in meters. Let's round it up to 300 million meters, but let's also put it in kilometers. So there's more, it will not do so much damage to our mind, to our brain. 300,000 kilometers. because a kilometer we can translate to a mile. All right, and we're familiar with miles. We're familiar with miles per hour. We're familiar with a mile more or less if we drive. Okay, so we know more or less where our home is, a few miles away. We have a feeling for a mile. I think it's about 20 blocks or something like that, city blocks, I don't know exactly. How many city blocks in a mile? More or less, 20. There you go. That was my intuition. Did I say 20? Yeah, that was an intuition. More or less. It depends on what city we're talking about, you know. Ancient cities have smaller blocks and so forth, but more or less, so you can have a feel for 20 blocks, right? For example, St. Thomas University. 37th Avenue is the current entrance. 32nd is the old entrance. So St. Thomas University is about 5 blocks wide. It's also about 5 blocks deep. It's about a square. So 4 times the width of St. Thomas, 4 times the width of St. Thomas would be 1 mile. It also means that our property is about 1/4 of a mile in length, right? All right, so a mile is 1.6 kilometers, 1.6. To make it extremely easy, you can round up to 2 kilometers per mile.
2 times 20 is 40.
40, yeah. All right, so 40 city blocks more or less would be
The speed of light.
2, no.
No.
No,
That you need
Let's-
to multiply by 300,000.
exactly. So what I'm trying to get here is 2 kilometers, all right? I want to convert this number, 300 million, into kilometers, because this is meters. We know there's 1,000 meters in a kilometer, all right? So 300,000 kilometers per second, 300,000, or about 200,000 miles, 200,000 miles per second. The speed of light, think of what I'm saying, the speed of light is 200,000 miles per second. If we are on I-95 in cruise control at 55 miles per hour, what is our speed? 55 miles per hour, okay? If we were to turn that into seconds, right? How many seconds in an hour? 60 times?
55?
Oh, 60 times 60. In other words, there's 60 seconds in 1 minute. That's the first 60. And then how many minutes in an hour? Another 60. So it's 60 times 60. How many seconds in an hour is 60 times 60, which is 3,600 seconds in an hour. All right. If we want to translate our 55 miles per hour into miles per second. But that's irrelevant at this point. That what I'm trying to get by this exercise is that that speed is incredibly slow compared to the speed of light. The speed of 55 miles per hour, which is relatively fast. I mean, you stick out your hand at 55 miles per hour, you feel a strong wind, right? 55 miles per hour for us, relatively fast. But that's nothing compared to 300,000 kilometers per second. Because think about this. We have a photon in the middle of our, we're holding a photon between our fingers here, hypothetically. All right. Now, let's see, what's 300,000? Let's think of a distance, an actual physical distance. Distance between what's the opposite city from Miami on Earth? Let's start there. The furthest away we can get from Miami is the opposite city, right? Probably somewhere in China. City from Miami. Oh, it's called the antipode. Yeah, the antipode. Interesting. Ah, Is it, it's the opposite side of the world. It's in the middle of the ocean, the Indian Ocean, but the closest city is going to be Denham in Australia. Okay, from Miami to Australia. All right, Miami to Sydney or something like that. Miami to Australia is called the antipode, the opposite, city, like the North Pole and the South Pole, for example.
Oh, okay.
All right, so that's the furthest. What distance is that?
19,000.
19,000. Let's round it up to 20,000. So 300,000, you know, it's out in space somewhere. The longest distance between any 2 points on Earth is 19,000 kilometers. That's the longest distance between any 2 points. We can round it up to 20,000. So 300,000, 20 into 300 is the same as 2 into 3 into 30, 2 into 30, which is the same as 1 into 15, 15.
Oh, 15.
20. 3 into 20, 300. 300 is, I'm trying to think how many times we would have to go around the Earth. No, forget the cat, please don't do that. Oh, yes. They're pulling their phones. Well, you're gonna be good in math by the time you end this program.
300.
Your mind will be scrambled. Okay, let's think about this. 300, so the furthest distance from one point to another on Earth, Miami to Australia or the North Pole to the South Pole, right? The antipode is being generous. It's 20,000 miles, 20,000 kilometers, 20,000. So I want to see 300,000. How many times we'd have to go around the Earth to get to 300,000? All right. So 300 divided by 20, which is the same as 30 divided by 2. Get rid of 2 zeros, right? So 30 divided by 2 is the same as 15 divided by 1. So 15. In other words, 300,000 kilometers, 300,000 kilometers is going around the Earth 15 times. All right. So now this is the mental experiment. I'm doing this because Einstein was a theoretical physicist, meaning that he never really set foot in a lab or do experiments. He would do mental experiments. He would have elevators falling, but falling, instead of falling against the Earth, falling out into space, accelerating into space. And that's how he came up with this theory of relativity, doing mental experiments. Years and decades later, those experiments were actually designed to occur physically. And then the physical, the empirical physicists confirmed his theoretical theories. All right, but he did mental experiments, which cost nothing except for a headache. All right, now we're all holding a photon in our fingers, between our fingers. We're going to release that photon. All right. It's hypothetical because it cannot be done, but we can do it in our minds. So we release the photon. In 1 second, what's 1 second? 101. It's 1 second, right? Remember when we used to play flag football, 1 Mississippi, 2 Mississippi, 3 Mississippi, right? Those are seconds. 101, 102, 103, 104, those are 4 seconds, right? Just to, because just 1 is a little too short. We have to put a little bit more wording. 101, 102, 103, 104, that's 4 seconds. So, ready, set, go, 101. All right. In 1 second, that photon has gone around the Earth 15 times.
In 1 second.
In 1 second, 15 times. In 2 seconds, it has gone around the Earth 30 times, and so on and so forth. You get the picture, right? So is that fast?
Super fast.
It's super fast,
Like
but
I understand.
exactly, it gives me a headache. But it's not infinite. In other words, if I let go of a photon, now let's put it in a straight line instead of going around the Earth, because actually I cheated a little bit. Speed can only be in one direction. If we make it circle, we're actually accelerating. We have to accelerate to maintain a constant speed because it tends to fly out by centrifugal force, okay? I cheated for the sake of just simplicity, but actually, if we release a photon, it would go straight, and in 1 second, it would be 300,000 miles away from us, 300,000 kilometers away from us. Okay, in 1 second. But you know, it's not infinite, which is very important because people think when you start thinking in these quantities, they're so immense that we start thinking, oh, well, then it's infinite. It's like in an instant, it's at the edge of the universe. No, it's at a specific distance away, which is 300,000 kilometers, all right, in 1 second. And in 2 seconds, and so on and so forth. But it's a specific distance, and it has been measured, and it has been measured down to the meter, as you can see here, down to the actual meter. All right. And so it is a specific distance and a speed, and it's therefore it's not infinite, it's finite, but it is humongous. It is immense. And so it belongs to that other category of the universe. Remember, this is from the course in Fundamental Bioethics, which the new court will receive. Yes, remember when I talked about the 3 universes that we move in simultaneously, the macroscopic, the normal macroscopic universe, which is more or less our size and things that we can see here on Earth, and even as far as maybe the sun, like a little dot there, which is a humongous star, right? Then there's a microscopic world where we need literally an instrument to see, like a microscope, and even further an electron microscope if we want to see molecules and things like that. And then there's the super macroscopic universe, which are the distances in the solar system and beyond, and the galaxies and the universe as such, right? The super macroscopic world. Well, this belongs in that category of the super macroscopic. There's a measure of distance, by the way, that is called a light year. A light year. How many of you have ever heard of that concept of a light year? It's a measure of distance, right? It's not a measure of time, because people think, oh, a light year must be time. It's not time. If you see science fiction movies, they make references of it, that light years away, all right? But it's just a humongous distance, because it is the distance that a photon travels within a year. So we would have to take 300,000 kilometers for every second, times 60 for 1 minute, times 60 for 1 hour, times 24 for 1 day, times 365 for 1 year. So 300,000 times 60 times 24 times 365. That's the distance. It's in several millions, all right? That's the distance that a photon travels in 1 year. And that unit of light years is what is used to measure the distance in the universe between galaxies and solar systems and nebulae and other phenomena out there, because the distance is vast, huge, but it's not infinite, it's finite. It's a real finite distance, right?
So, but they can really, with this super microscope, can they really see that light?
Telescope, they cannot see the light, they can see the effect of the light.
Yeah.
The effect
That's
of the light.
why they said, for instance, when they, like the meteors or whatever.
Yeah.
Like, what they say is after what it happens is that I don't understand.
The effect, we see the effect. They travel very fast. Well, meteors, asteroids, we're getting hit by them all the time, but thanks be to God to the atmosphere that is a shield, and that is gas. So what happens to those meteors and asteroids as they're coming our way, they burn up. And so we just see the effect of that burning, which is a streak of light, right? Which is a release. There's also heat and so forth. And every now and then, some fragments may hit the Earth. Those are the meteorites that are found here. But the Earth and the Moon have more or less the same age, which is about 4.5 billion years. And look at the Moon, how it looks. On the surface, it looks like Swiss cheese, right? we should look the same were it not for the atmosphere that shields us. So the atmosphere is shielding us from the shower of meteorites and asteroids that we're getting all the time. We should look like the moon, and we don't.
I understand, but like they were saying, for instance, that the comet
Yes,
that we see,
right.
we have seen something that happened like 20 years ago. Is that what they're saying?
Okay, so there are some comets, and we'll get into that very briefly when we look at the cloud or ring of meteorites that are out there, asteroids and comets, right? And periodically, they come near the orbit of the Earth. And so we can see them, but they don't actually touch the atmosphere. They come near so we can see the little streak, but they keep going, like that famous Halley's Comet that has its own orbiting. And periodically, every few hundred years, it can be seen. I think the periodicity is about 500 years or something like that. All right, those are comets. Okay, so, but the bottom line about this formula is that you see that this, the c, which is the speed of light, the constant speed of light, 300,000 kilometers per second. It's a humongous number. Now square that, right? Meaning 300,000 times itself, times 300,000. All right, it's 9 gazillions, yes. Mentally, we'd have to put 9 zeros plus 9 0, 18, 9 and 18 zeros. Okay. That times the mass, as small as the mass is, it could be a tiny little mass. That's the energy that that mass has in it, potential energy. Potential energy. All right, so a grain of sand sitting on our palm, which we can barely see with the eye. Think of the smallest thing that we can barely see. It would be a little tiny grain of sand, right? Or a single grain of a crystal of salt or pepper, whatever you want to put on the palm of your hand, a single grain. That has a humongous amount of energy stored in it as potential energy. And that was the big insight, the discovery. So yeah, everybody can quote, even elementary school kids can see, oh yeah, E equal MC squared. Now what's for lunch, you know? Because they have no clue what we're saying. Every piece of math has an incredible amount of energy stored in it. Potential energy, atomic energy. So you know where I'm going. When we split the atom, we get the release of that energy and we get a nuclear reaction. We get a nuclear bomb. So the nuclear energy that is stored in each atom is enough to blow up an entire city with millions of people as a nuclear bomb, or light up that city with a nuclear reactor that is running the electricity for the city. Extremely powerful. So that just means that a little mass has a lot of energy in it. Okay, now compare the mass of the whole Earth to a single grain of sand. How much potential energy do we have stored on the Earth? And this is just one of the 8 planets that make up our planetary system. And our planetary system, which we call the solar system, is just one of millions of solar systems that are in the Milky Way, which is our galaxy. And the Milky Way is just one of millions of galaxies that are out there moving around in the universe. So you see that the amount of energy that is in the universe is beyond humongous, but it's a specific quantity. Okay. Now, back to slide 2 on our lecture. Oh, sorry, slide 3. Wow, making progress. It turns out that, so that's what we call the mass energy equivalence. Okay, so really for physicists, you know, physicists are so weird that they can think about this bottle and the liquid inside in terms of its energy, or its fluidity, or in terms of its contribution to the total mass or energy of the universe, and so forth. You know, but basically, all matter energy together that is visible. I'm using the term visible and dark in quotations because I'm using them by analogy. All right, visible energy and matter together. By visible, I mean measurable, all right? It's only about 5% of the universe. All of the mass and energy that we can measure, which includes all of the galaxies and all of the planetary systems in the galaxies, including our humble little Earth and everything that's on it. It's only 5%.
So
These are
saying
estimates.
Only 5% of what that we can see. That's it.
That we can measure at least.
That we can measure.
That we
what
can measure.
see.
Well, we can see it through an instrument, you know, because think of a black hole, for example. You know, we can't really see it, but it's there. That makes up what we call dark matter. So 5% is matter slash energy. We know that they're interchangeable, of what we can measure with an instrument, with an actual instrument. The other 95%, because we cannot measure it, we call it dark, in quotations, because it's not accessible to, at least to the instruments that we have today. Now, of that 95%, 27%, almost a quarter, a little over a quarter of the universe is what we call dark matter. Now, dark matter, we have an indirect measurement. We have an indirect approximation. I mentioned black holes. Black holes, essentially, what is a black hole?
I guess it's where the light cannot be penetrating.
The light does not exit. Imagine.
Exit.
Right. So a black hole is a gravitational system. A black hole is a gravitational system that is so dense, the gravity is so dense that not even photons are able to exit. They're being sucked in, they're being pulled in, all right? So all matter and energy that goes around a black hole gets sucked in. And that's why it's called black, because we can see it. And here is an actual photograph of the universe. And all these little dots, typically we call them stars, but not real stars, they're actual galaxies, galactic systems going on, right? But they're so far away from us that they look like a single dot. Just like when you take two flashlights and you move them far away, those two dots start getting closer to each other. At some distance far away, the two flashlights look like they're a single source of light, all right? So these little dots that we call stars, typically they're galaxies. Doesn't matter, they're just far away. And you see that there's a cluster of, there are clusters, right? They're scattered, let's say it's a pattern. We could call, for the sake of argument, let's call this a random pattern of little white dots. But look here in the center, there's no white dots. It's blank. Why is it blank? Because there's a black hole here. And there's a black hole that is sucking in all the light within it, because it's sucking in entire solar systems that obviously have light of their own, because the solar system is essentially a gas giant that is on fire, right? And giving off light and heat, but cannot be seen because the gravitational density is so thick that is pulling everything in. And then it also causes what is called a lensing effect. A lensing effect is the light that is from behind. The light from behind is coming through and it's reflected like a lens, right? Because of another field that establishes out there at the periphery of the black hole that causes a lensing effect. A little bit of a lensing, kind of similar, somewhat parallel to when the sun sets. Not only does it go from bright yellow, almost whitish yellow at the azimuth is above our heads, you know, to the horizon, it keeps losing brightness, right? And turning more yellow and toward, eventually toward orange, and also gets bigger. Is the sun actually losing, turning orange and getting bigger physically, the actual sun itself? No, the sun is still the same ball of gas, of heat, of hydrogen that is on fire, the same size, you know. But what is happening is it's going, the rays that are coming toward our eyes are going through more and more atmosphere, because think of the atmosphere as a lens that is around, right? There's actual gas there, the atmosphere is gas, so it is reflecting and refracting the rays of the sun, and the net result is it acts literally like a magnifying glass. It makes the sun look bigger and less bright, moving, shifting on the spectrum of color, on the visible spectrum, from yellow to orange and eventually to red, almost reddish, right at the very end of the sunset. What is left just a little sliver, it's a reddish orange, you know. So you see, that is a lensing effect that is occurring because of the atmosphere. Something kind of similar occurs with black holes, and that's how we can tell they're there. But it's indirect measurement. It's the effect. Lack of light at the center of the hole, because no light is getting out, and a lensing effect around the perimeter that defines a black hole from the light that is behind the black hole that should be coming straight through, but is being diffracted or reflected and refracted around the black hole because of the gravitational system that is there. So those are black holes. And you can imagine when two black holes start getting close to each other, what's going to happen? They're sucking everything, and they're sucking themselves also. So there's going to be some kind of interaction.
One is an eat the other one.
Eventually, one will eat the other, or the two will collapse into one. And there will also be streams. I mean, the phenomena that occur are just gigantic, almost impossible to think about. They're jets of energy that spill out perpendicular to the rotation to the plane of motion or rotation. And there are other phenomena that occur. This is so energetic, and that's why it's being painted in color so we can see it. So it's being colorized, but it's like a cell. When we see a cell on a microscope, it's translucent, you know, and it's transparent. We dye the cell with different tints, with different dyes to see different parts of the cell. Otherwise, the organelles look transparent. We can see through them. All right, similar here. But eventually, we can conceive hypothetically that black holes coming together will merge and absorb and become a more larger, humongous black hole, which will absorb more because it has more gravitational pull and so forth. And we can conceive eventually, perhaps, that the universe will end in one humongous black hole, being everything sucked in, back to where we started, which is the point of singularity, where all mass and energy condenses into a single point, a mathematical point, which is kind of scary to think about. It will take a few 100,000 million years for that to happen. And so hopefully we'll see it. I plan to see the show from above. Okay, in full detail, but not here.
Today,
Yep.
there is a kind of a concern in the scientific world about the black holes getting closer to us. Is that real, or is that
It's real. But again, they move extremely slowly. We're extremely slowly, meaning that the distances are so huge that we have nothing to worry about. It's certainly beyond a human life. I mean, 100 years is a long life for a human.
I understand that. However, they just discovered this recently, and this is why I'm just thinking in terms of the scientific work, black holes were relative and new discovery because of the possible equipment that we have now.
Yeah, the Hubble telescope, basically, which was, I think, in the 50s.
That is why maybe there's a concern, because before they were always been.
Yeah, right. But now we can see them indirectly. Yeah, and we know they're there.
The other question I have is a little, I'm sorry that I but
Going.
NASA is going to send this rocket, supposedly to hit this asteroid. How serious is that really for us?
Well, it's serious for the asteroid, but not for us, and it's more serious for the rocket.
No.
Yeah. So the short answer is I don't know. I'm really speculating a lot because it's not my field at all. All right, but this is basic things. Say?
Yes, just a point. The closest black hole to us is actually the center of our galaxy.
Oh, there you go. Yes. Thank you. Yes. Thank you for reminding me that, because yes, now it's estimated that basically galaxies at the center, galaxies are really a black hole system. And that's why they gyrate and they have that planar, when you look at galaxies, that they're represented like spirals. And more we're discovering that at the center of galaxies is a black hole. So really the bigger picture is that we're all hovering around the black hole. And it's only a matter of time before we get something.
So it's not the sun now, it's the black hole.
Yeah, but the sun is just one little dot within the Milky Way, within the millions of, all right, Milky Way.
Dr. Martinez, thank you for
Yeah. There's a little more to worry about. Don't lose any sleep on this, okay, folks? Now, the Milky Way has been photographed, as you can see there. These are actual photographs. And it's not too evident from these photographs that there's a black hole there at the center, but there is. Because there's so much luminosity of so many suns. And you see, it's got millions of solar systems. Each one of these little dots, I always mess it up. Each one of these little dots is a solar system, okay? And there are millions of them. This is the Milky Way.
And this has been done with the telescope?
Yes, the Hubble, and now, of course, the James Webb is going deeper and deeper into space to see energy, mass and energy that is further away toward what is called the background radiation. The background radiation was supposed to have been released at the beginning of the universe, and that's really what I wanted to get with slide number 4 here. But for going there, so dark matter, bottom line, is the matter that we cannot see directly or we cannot measure directly, and it's 1/4 of the universe. And it's mostly the matter contained within black holes that is generating these humongous gravitational fields that is sucking everything else around them to a certain distance. Because see, the other thing about gravity is that it's an extremely weak field. Actually, it's a weak force, thanks be to God, that is weak. Otherwise, we'd be nailed to the floor, we couldn't move. Right? So gravity is a relatively weak force, but it's real. So that's now dark energy is the other 1/3, more or less, of the energy in the universe. Okay. And this energy is called dark because in the words of a philosopher of science, we have no clue. We're in the dark as to what it is. All right, we're in the dark. In other words, it's not light energy, it's not electrical energy, it's not heat, it's not radioactivity, it's not microwaves, it's not sound waves, all of the different types of energies, it's none of those, because all of those we can measure. And this guy, we can't measure. And it's about 2/3 of the universe. So that's the challenge and the excitement, you know, and it's an estimate. And it's an estimate mostly from what is known as the background radiation. Because when we add the 5% plus the 25% plus the other 2/3, you know, we're supposed to get 100% here. And the 100% is what was at the moment of the Big Bang, of the origin of the universe. And still is, only that there have been 2 moments since the origin of the universe. One has been incredibly fast, and the other one has been incredibly slow. So the first moment after the Big Bang is called inflation. The second moment is called expansion. So the first moment is incredibly fast, within nanoseconds, was formed what is known as the background radiation or the microwave background. Cosmic microwave background is the actual term. All right?
You mean the first moment of
the Big Bang. What happened? We can ask, yeah, the origin of the universe. What happened after? So the origin is a single event, right? What happened seconds after the origin of the universe? After the origin of the universe, what happened within seconds was an incredibly fast expansion, or sorry, inflation. And that happened within seconds. After that came a second phase, which is called expansion. And that one is measured in millions and billions of years. So the contrast between seconds and billions of years are like the 2 opposite ends of the time scale. All right. You can see at different stages of the expansion. First, there's the cosmic microwaves. Atoms, by the way, form the various elements, beginning with the first one of hydrogen. And as atoms are colliding, they're forming heavier atoms, right? And then as heavier atoms are also colliding, they're forming molecules and so forth. And eventually these molecules keep coalescing into planetary systems or into solar systems. Now, matter, don't forget that matter is in 3 states, actually 4 states, but the ones that we're familiar with is solid, liquid, or gas, right? But gas is also matter. So the sun, which is a ball of hydrogen on fire, is gas, but it's matter, it's mass, and it has, if it has a mass, it has a weight also. All right, so planetary solar systems form and galaxies form, and eventually we get to the current universe that we see, and that took 13.7 billion years. So again, you can round it up to 14 billion years if you want, 14 billion, which is 10 to the 9. A million is 10 to the what? A million is 10 to the 6, right? 1 million, 1 and 10 zeros, right? And 6 zeros. So a billion is 10 to the 9. It's another 3 zeros. That's a billion. A trillion is 10 to the 12 and so forth. However, those numbers get so big that we don't even agree on the name, because what we're calling a billion, which is 10 to the 9, actually the Europeans call it 1,000 million. All right. And then what we call a trillion, they call it billion. So for the Europeans, a billion is a million million. But for us, a billion is 1,000 million. So those numbers are so huge that we cannot even agree on a name for them. And that's why we need to use scientific notation because the numbers don't lie. So it's either 6 zeros or 9 zeros or 12 zeros, okay? But the numbers are specific. So when we use scientific notation, 3 times 10 to the 9 or 13 times 10 to the 9, it's the same number no matter where we are on Earth. Anyway, the age of our universe has been estimated to be 13.7 billion years old, right? Which means that 14 billion years ago, there was nothing. And it's nonsense to talk about 14 billion years ago because time didn't exist either. Neither time nor space, because there's a time-space connection, right? If there's no time, there's no space, and if there's no space, there's no time either. So to say 14 billion years ago is nonsense. We can only talk about as far back as 13.7 billion years ago, give or take a few million years of margin of error. Interesting. All right, anyway, moving forward, we're almost there. This is further detail. I'm not going to go into it, but you can see what happens. The seconds, you know, here is, where's 1 second? Here's 1 second, all right? If we go less than a second, this is 1 millionth of a second because it's 10 to the 6 seconds. So this is 1 millionth of a second, 1 millionth of a second. This is 1/32 of a second. This is 1/43 of a second. Okay, then going forward, you see the scale is not to scale, it's accelerated because this little fragment represents 3 minutes, whereas this other little fragment, equivalent, represents 300,000 years. It's just showing the beginning of solar systems, and then 1 billion years, and finally 15 billion years puts us out of scale. Again, it's nonsense to talk about 15 billion years because we're not there yet. All right. You can see first subatomic particles, and even subatomic particles are made up of subatomic particles, like protons are made up of what we call quarks, and the quarks get very quarky. That's why they use the name quark. They have funny names like top, bottom, and color and flavor and things like that. That's the quantum physics field. They eventually coalesce into making the subatomic particles, the classical ones, protons, electrons, and neutrons, but also the counter particles like the positron, which is a positive charge instead of electron, you know, but negligible charge and so forth, and all the other, and the photons and so forth. Eventually they coalesce into forming actual atoms, which is a stable unit of life, of matter. And then atoms will coalesce to form molecules and so on and so forth. Eventually, 13.7 billion years later, we get the universe that we know today. Now, just very briefly, I want to talk about the planetesimal hypothesis. First, we have these huge balls of gas, which typically are on fire, right? Of mostly simple atoms like hydrogen and helium and so forth. When they start cooling, because heat radiates, right? Heat radiates. If I have a candle that is lit, there is heat all around the candle, and I can feel heat all around the candle. That's called radiation, right? It radiates, heat radiates, just like gravity also radiates out from the source. As that heat dissipates, that object, that gas on fire starts cooling. And eventually, as it starts cooling, the atoms start coalescing into molecules.
Dr. You said that you're not, you lost the connection.
Well, I'm still on. Did everybody lost the connection? It could be his connection. Can someone hear me? Someone open your mic and say yes.
Yes.
Father, yes.
Okay, then it's local. Thank you. All right. So as these huge balls of gas start cooling by heat dissipation, right, which is known as entropy. It is energy that is unavailable for work, entropy. There's an increase in entropy in the universe of radiated heat. Then these gas giants start collapsing, and as they collapse, those atoms are forming molecules, and those molecules are getting bigger and larger and forming larger complexes. So there's more gravity building within at the core, right? And that gravity is going to be pulling in more of the molecules that are around. So at some point they collapse and then they explode. So it's a cycle of stars that they collapse with time and then they explode. As they explode, they form kind of a plane, which I don't know exactly why, but they form a plane now. And that is known as the planetesimal hypothesis. This plane also starts gyrating or rotating because there's gravity at the center. And the gravity will keep these massive objects rotating around, and eventually those massive objects, they're generating their own gravity, right? And they're pulling in matter from around them. And that matter could be just asteroids that are kind of flying together around, but then the bigger asteroid will pull in smaller ones and coalesce. Everything is red hot or white hot, so things are melting together in a molten state. They pull in more matter. Eventually, they become planets. They become planets that kind of stabilize. Some will fly out into space. Some will get sucked in by the star, by the sun, and collapse into the star. But some will actually start developing an orbit that is stable. Stable orbit meaning that the gravitational pull is counterbalanced by a centrifugal force. Centrifugal force meaning that the planet constantly is tending to fly out into space at a constant speed, precisely, and not in a circle, right? Not describing a circle, but at a constant speed, which is a straight line. But because there's gravity pulling on it, then is the vector between two forces. Gravitational pull is down toward the center, whereas what is known as a centrifugal force, the planet tends to fly out into outer space at a perpendicular distance, like a tangent on a circle. And the vector, the end result between those two forces, one pulling this way and the other pulling that way, the end result is in the middle. It's a vector. And the middle is precisely the tangent that describes the orbit of the planet around its sun. All right. And like I say, those that become stable, and they develop an orbit, which doesn't necessarily have to be a circular orbit either. Typically, they are elliptical orbits. So at some time, we are closer to the sun during the year, and then sometime we're further away from the sun during the year, and that marks between summer and winter, right? Now, so they're elliptical, but still stable, more or less, so that within thousands or even millions of years, that orbit is maintained. All right. And that's eventually what forms the planetary system. And that is known as the planetesimal hypothesis. All right. There are many more details to it. Don't worry about it, please. I've gone into too much detail already. But basically, at some point within that for our system, for our planetary system, which is basically the Milky Way within the galaxy of the Milky Way, took about 4.5 billion years. So the last 4.5 billion years. So you take 13, if we want to make the numbers simple, you take 13.5 and you subtract 4.5, you end up with, quickly, 13.5 minus 4.5, 9. Because 9 plus 4.5 is 13.5, right? Come on. All right. So our planetary system basically started forming about 9 billion years after the origin of the universe. And it took 4.5 billion years to form, and here we are today. All right. So our solar system, all this to place Earth within the context of our solar system. Our solar system has basically 8 planets. Yes, because what's its name? Pluto here was downscaled to a dwarf planet. Yes, to a dwarf planet as opposed to a normal planet. Yes, and Pluto has its own orbit that is not necessarily. Yes, 8 planets. The 4 inner planets: Mars, Earth, Venus, and Mercury, which also happen to be smaller. Yeah, and then there is an asteroid belt there. And then the 4 outer planets, which are also known as the 4 giants. They're mostly gas, and they are Jupiter, Saturn, Uranus, and Neptune. Okay, and then Pluto now has been downgraded to a dwarf planet. And has its own orbit, but it's not the same circular or elliptical orbit that the 8 classical planets have. So that's why it's thought that Pluto was coming from outer space and got trapped into the gravitational pull of the sun somehow. All right, but Pluto has its own orbit that's very weird. Anyway, there are 4 other planets, dwarf planets. Ceres is one here that is near, it's on the inside of the asteroid belt. And then there's another one that is near Pluto. Then there's Makemake. Then there's Haumea, which is a little tiny one here. And there's Eris that is on the outside of the second belt, the second asteroid belt, which is known as the Kuiper belt, all right? And it's out here. And so it frames, these asteroid belts kind of frame the inner planets and the outer planets. And the whole of it is our solar system, what we call our solar system. And our sun, which is another word for a star, which is a gas giant. No, this is just one dot. Don't confuse your scales here. This is the Milky Way. This is the Milky Way. Our solar system, this guy, all of the system put together. The sun plus all the planets around it and the asteroid belt and all that put together as a unit is only one dot of the millions of dots here. So there are millions of other solar systems in our galaxy, which we call the Milky Way, because from the Earth, it looks like this. It looks like a streak. I've actually seen it once up in the mountains in Spain. I saw it was a moonless night and the Milky Way was evident, and we actually got a star shadow. You know how you can get a moon shadow on a full moon at night out in the countryside where you don't have reflection from the ground, right? You can get a moon shadow. Well, that time in Spain, about 60 years ago in my life, up in the mountains, Picos de Europa, which is a mountain range up in northern Spain, I was there with some other people, my parents and a group of people. And it was a moonless night, and we could see the Milky Way because there were no city lights around, clear across like that, like a literally river of shining lights, right? And we can see our shadow, which is a star shadow from this. It's a rare phenomenon. Anyway, so see, these are different solar systems on this one, right? We're in here somewhere. Yeah, wow is right. Okay, back to our tiny little, and see, here we are, here's the moon. All right, so this is us, the only planet that we know of that has liquid water so far, which is the basis of life. And this is really where I want to get to. Okay, one last theory before we actually look at the geosphere, which is this process of accretion. All right, so accretion is sorry. Question coming? Okay, accretion is basically as massive objects, and a massive object is anything that has mass, right? But we can use massive object in two ways. Anything that has mass technically is a massive object because it's made up of mass. But normally when we talk in common language, when we say a massive object, we're referring typically to something as small as a planet or as large as a sun or a star or galaxy. Those are massive in the connotation of the word huge. All right. So the planets were formed. The planets were formed. Who is it this time? Farid. And Father Daniel, please mute your mics. Thank you. Okay, so accretion is a process of sucking in by gravity other objects that are flying around. Okay, so that's how a planetary system formed. The Earth and the other planets on our solar system, they form by this process of accretion. And that's what eventually took about 4.5 billion years for the planets. And so the first event is actually accretion, which is pulling in a massive object that is pulling into itself by gravity other objects that are flying around and are striking the massive object. They're melting within it. You know, this is red hot, or better, white hot. When we light up a stove, an electric stove, it turns red hot, right? That's pretty hot. That can burn. But if we keep heating those coils, eventually we can turn it into white hot. In other words, beyond red, white, when it actually glows and it's giving off photons, just like the old incandescent lights, the little filament inside turned white hot, right? Because it was heated so much that it started giving off photons. And that's why they were hot. When you touched the incandescent bulbs and tried to change it, when it went out and you had to change it, it would stay hot because it was so intensely hot, thousands of degrees of temperature. All right, so that's the process. And then there is once the accretion has completed, then it goes into differentiation. Differentiation is forming various layers according to the density of the mass. All right, so we know that the most common element on Earth is what? Without it, we become anemic. Hint. Anemic.
Iron.
Iron. Takes a doctor to tell us, come on. Iron is the most common element on Earth, all right? And it's at the core, it forms the core. Also nickel is there, right? And imagine, this just came from elements that were flying around the universe that coalesced through the expansion process into rocks and asteroids and meteors and all that. They started impacting each other and globbing together. As they glob together, of course, they become more and more massive. With more mass, there's more gravitational pull. So this is kind of the mass equivalent of a black hole. The process of a black hole, but not yet, not quite. This is very tame compared to the gravitational pull of a black hole. So the density is different. And the massiveness is also different. So on a small scale, very tiny, tame scale, we get planetary systems, all right? And we get what is known as an inhomogeneous accretion. Again, a big word, fancy word for, it just means layers, different layers of the Earth. So that we have three main layers today. And two of those layers are subdivided into two more layers, right? So from the outside going in, we have the core, then we have the mantle, we have the crust, the mantle and the core. Those are the three main layers: crust, mantle, core, right? And the mantle and the core are themselves subdivided into the solid core and the inner core and the outer core. And then the mantle is also the inner mantle and the outer mantle. We'll get to it, but basically that's what means inhomogeneous. It means that between layers, it's not homogeneous, but within the layer, it's more or less homogeneous. So let's say the core, which is mostly nickel and iron, is fairly homogeneous, homogeneously made up of nickel and iron. But when we leave that layer and go to the mantle, we have a different type of homogeneity. We have basically rock, soil, many other elements in a molten state, in a liquid, thick liquid state that when it spews out, we call lava, right? And it's not only liquid and not only nickel and iron, it has many other elements and molecules in it. That's the mantle. Finally, we get to the crust, and the crust is mostly the rocky layer that forms the Earth, about 10 kilometers thick, more or less, various thickness throughout the Earth. But that's basically where the continents are, and also the bottom of the oceans. Also, the distance of the Earth to the sun is such that it allows for liquid water. Now, again, the 3 states of matter, which is actually 4, right? So we got solid, liquid, and gas. What's the 4th state? Well, the condensation is going from, it's actually phenomenal, going from gas to liquid, but plasma state, the plasma state. What's plasma state? The sun is plasma state. The fire of a candle is plasma state. You know, it's real, we can measure it, right? We can see how hot it is, we can see how many photons, how bright it is, but it's unstable. And that's why normally we're talking only about 3 states of matter: solid, liquid, and gas. We can go from one to the other by increasing or decreasing temperature, right? Heat. Or we can also go from one to the other by increasing or decreasing pressure. So temperature and or pressure, right? But there's that 4th state, which is plasma. But plasma is unstable for us in our planetary system, okay? In our Earth system. But it's real. And the sun is an example, stars in general, and also light, fire, okay? That's plasma. All right, so we're at a distance from the Earth, from the sun, that it allows for liquid water, which means that the temperature gradient is between 0 and 100 centigrade, which is a very narrow temperature range where we consider the temperatures of the universe, all right? The minus hundreds of degrees or the plus hundreds or thousands of degrees on either side. Well, we happen to be at that distance that allows for liquid water. And that's important, very informative, because water is the basis of life on Earth, the organic basis. Right? In other words, if you were solid water, ice, we cannot have water, we cannot have life from ice because the molecules are essentially, we cannot have chemical reactions. Everything is on a standstill. And vapor, water vapor, the molecules are flying all over the place. First of all, it's too hot, but there are some bacteria that actually live in boiling water, all right? They're called extremophiles. We talked about them once. But water vapor itself does not allow for an orderly fashion of chemical reactions, of metabolism, because their molecules are essentially unrestrained, they're flying around. Vapor, that's what it means by definition, gas. The molecules take up the size of the container. They're not restrained, all right? For metabolism, for orderly chemical reactions, we need a stable environment, which we call liquid. And the liquid for us is water, the universal, the almost universal liquid.
So Mercury and Venus cannot have water because they're closer to the sun.
They have water, but it's not in liquid state. You have to think of either the boiling water for your tea or the ice cubes in your refrigerator.
I understand.
Okay.
I guess I do. Mars potentially could.
Could, but underneath. Okay, because let's go back to where the planetary system was. Yeah, here. Okay.
I was looking at it, yes.
At the surface, Mars is too far away from the sun. So at the surface, it's too cold. But it could be because the core of Mars is hot. Just like our core is hot. Our core is quite hot. It's thousands of degrees hot. You know, it's 6,000 degrees hot at the core of the Earth. So underneath the crust is hot. That's why lava is hot and not cold. So underneath the crust, there could be liquid water, or somewhere in the crust of Mars, there could be liquid water. but it's not exposed to the surface. All right. The opposite is true for Venus. At the surface, it's too hot. So water evaporates at the surface of Venus. But maybe inside Venus, it's cooler, somewhere in the crust, and they could have liquid water there. In fact, I think one of those two, they have discovered the oceans. They talk about oceans. I don't know if it's Venus or Mars, but actual liquid oceans that are underneath the crust. Now, whether there's life in there or not, that's a different story. But there is liquid water, some indirect measure that was done that discovered these oceans. Interesting, exciting. All right, the layers of the crust for the geophysics, but more important is the continental drift that we're going to talk about in a few minutes. I see it's 11:30 already. So let me get to continental drift and we'll stop there, okay? I'm going to accelerate a little bit here because I just took too long to go over this. All right, let's look at the layers of the Earth. This is more to scale, as you can see. Here is the core, the two cores, the inner core and the outer core. You notice the temperature is extremely hot, so hot that the inner core is actually white hot, right? The outer core is already getting to yellow hot. By the time we get to the mantle, we are at the orange hot, like lava looks orangey when it comes out, right? So it's orange hot or red hot as it's losing heat. So we got the two layers of the core, then we got the two layers of the mantle, the inner mantle and or lower mantle and upper mantle. And then finally the crust, which is a very thin layer compared to the whole thickness of the Earth. Okay. It's only, 100 kilometers. I was wrong, I said 10, but it's about 100 kilometers, depending on where we are. Of course, on the bottom of the ocean, it's thinner, and on top of mountains, it's a thicker crust. But it's a very small scale when we compare 6,000 feet to the core, 6,000 kilometers. So that's the composition, what we call the geosphere, right? But the geosphere is also dynamic. It's dynamic in that the crust has these continents, the 7 continents, right, that are on top of on the surface of the Earth, but they're also moving. But they're moving very, very slowly. So it's only a few inches or centimeters per year, but it's significant. It's significant because the continents are moving, are shifting. And you can think of it more or less as a raft on top of water, right? A raft on top of water. What is the raft? The raft are the continents that are sitting on top of the mantle, because the mantle is lava, is molten rock. So it's a thick liquid. It's liquid, but it's thick, but it's liquid. And so the crust has been stabilized, all right, in geologic time, but it's still shifting a little bit. And that's what's causing the volcanic activity and the earthquakes that occur, especially in certain parts of the world, which are the edges of the plates, of the tectonic plates. And that's where we get the theory of continental drift. First, how do we know about these layers? I mean, who has ever gone down there with a thermometer to measure that? We don't even have a thermometer that can measure that, right? Well, it's done by precisely measuring the reflection and the refraction of shock waves from earthquakes. On one part of the Earth, measured at the epitope on the other part of the Earth. So here's just a diagram that shows that. Let's say it's an earthquake here on the top, and the reflection and the refraction of that shock wave as it moves through the crust into the mantle, through the mantle, which is a thick liquid, and even through the core, which is a solid, because waves can move through cores, right? Eventually, it will hit other parts of the world, and there are seismometers in different parts of the world placed strategically to measure the delay, the intensity and the delay of those waves when they get there. So we know the initial, the epicenter where the earthquakes originated, and because there were the metrics that measure that epicenter, seismometers, there were seismometers there, we can measure the intensity, the duration of, and the origin of the wave, right? And then how long it takes to get to other parts. We can figure out the thickness of the mantle and the density of the mantle and the size of the mantle and the core. And that's how it's been done. And that's how we can come up with this plan. And this is an actual illustration here of how the waves are measured. You see, this is data that has been picked up by we call the seismometers that measure the tremors of the earth. Okay. Well, all kinds of tremors. It's just that in order for the wave to be able to go through all the way, you need a relatively large earthquake. I mean, there are tremors going on all the time, but are minor, we don't even feel them, right? But they're going on. But to be able to be measured at the other side of the earth, it needs to be a substantial earthquake, you know, probably something on a scale of 5 or above on the Richter scale. Okay, so that's how I measure. Just to say that this diagram of the earth and its layers is not just pulled out of the hat, you know, by fantasy. It's real, and it has been constructed by doing this kind of measurement. All right. More details about the thickness and the temperatures and so forth. Not to worry about it. We're going to stop here because I've been torturing you for 2 hours now. And we're going to go into now the theory of continental drift and convection currents and plate tectonics and all these keywords. All right. So if there are any questions or comments, make them now. Otherwise, we're going to go into a little break. 11:35. I'm going to start at 11:45. Okay, so we got 10 minutes. Let me pause the recording. USI. Pause. Okay, folks, welcome back. We're going into the second half here of today's lecture. We're going to speed up a little bit, okay, and hopefully keep it within an hour or less. Just check briefly. In case someone has a question, no. All right, so we're going to be looking at this part here of continental drift. So what is known as plate tectonics, a plate meaning more or less a continent, all right? And also seafloor spreading, what is meant by that? And what is causing all this movement of the continents is something called convection currents. Convection currents occurs in liquids as liquids move and flow in a particular dynamic that is generally perpendicular to, or rather parallel to the pull of gravitational pull. We'll see what I mean with this little video. Oh, I have to optimize, see, optimize for video clip. Yeah. Now, this fellow has a little dramatic music in the background, you know, but he tries to dramatize it, but he explains the process very well. It's very short.
Take a deep breath. Get ready for one of the most hypnotic things you'll ever see in a science class.
So there are two dyes, blue and red, in water.
Have you heard that heat rises? Well, here you can see it's true for yourself. I've got some food coloring on the bottom of a plastic container, and there's a hot mug right underneath the red food coloring. As it's heated, the water rises. But I want you to look closely and notice something else. The blue on the sides is being drawn in. You can see it better when I speed it up. Here's the thing I want you to remember. When water moves from one place, it doesn't leave a void behind. Water from somewhere else has to move in to take its place. That's why you can see the blue food coloring coming in from the sides. You can see it better from above. Watch that blue food coloring get drawn in. Do you see it? The hot water reaches the top, and then it gets pushed toward the edges by more hot water rising from underneath it.
Let me stop for a moment because it's not too evident. He said it a little too fast. At the bottom of this liquid container, he's got three mugs. You can see this is one mug on the left, another mug on the right. And then in between, he slipped in a middle mug here that has hot water inside. And so that's the heat. This mug is just water that he heated up in a microwave or something and slipped it in underneath to generate heat. That's all. And that's why it looks a little water vapor. You can see water vapor condensing here on the outer surface, all right? But that's just a source of heat that is making the dye, whether red or blue, the dye move up because it's following that motion, which is called a convection current.
As it goes out to the edges, it starts to get cool, and cool water sinks just as hot water rises. And if you watch really carefully, you can see it sink and get drawn back toward the middle. These are called convection currents, and you see them moving here in two big ovals. They're one of the major things that drive ocean currents, especially in the deep oceans. But it's not hot water rising that drives the ocean currents. It's really cold water sinking up near the poles. Here's a piece of ice that I froze with some blue food coloring in it, so you can see how cold water sinks. As water sinks at the North Pole, for example, water has to flow up from southern regions to take its place. And these currents travel around the globe, some of them taking 1,000 years to complete their course. Understanding convection currents will help you get a grip on weather systems and the movement of Earth's continents over the eons, and even the workings of a lava lamp. If you want to try this for yourself, click on this link for all the directions you'll need. Thanks for watching.
Okay. So you understand now what convection currents are, and it occurs on the hydrosphere, meaning the ocean currents. It occurs in the atmosphere, making the weather pattern systems that we have. But it also occurs on the mantle. In other words, any fluid will form these convection currents. And because the mantle is molten, is liquid, thick liquid, it's also moving by convection currents, all right? And that's what's causing the continents then to drift. So we have the mantle that is hot near the core will move up. As that mantle flows up, it gets to the surface, and it has nowhere else to go, so it goes sideways along the base, the bottom of the continents, of the crust. and it will go sideways. And as it does go sideways, there's a transfer of heat through the crust to the oceans or through the continents out into space, because the Earth is radiating heat out. So as that part of the mantle loses heat, it gets cooler, and eventually it drops, it goes down because it's now cooler. And as it cools and goes down toward the core, coming in contact with the core or near the core, it gets hot again. It's heated up. And so there's this transfer of heat by convection currents from the core, through the mantle, through the crust, out into space. And that's how the Earth radiates heat out, right? It's a physical, mechanical thing. But the long and the short of that is because lava or the mantle is molten, is thick liquid, it is actually displacing the continents. From the bottom, it's like coming up to a raft from the bottom of the water and moving it around, okay? And so it's moving, it's displacing the continents. But the continents are part of the crust of the Earth. So they have a limited place where they can go sideways, and they start bumping into each other, and then they start colliding, and one continent will go on top of another, right? That's, let's say, at the bottom of the crust. But on the top of the crust, also continents, when they, these plates hit each other, they buckle up. It's like taking two pieces of, say, soft cardboard or something and pushing them against each other. They're going to buckle up like that. What does that form? That forms mountain ranges. All right. Now, this is over thousands of years and hundreds of thousands of years, which is geologic time. The long and the short is that we get all this activity, geophysical activity on the crust of the Earth, right? In some places forming mountain ranges, in other places forming ridges and ravines that go deep into the ocean floor. And also even mountain ranges in the middle of the ocean, right? That are much bigger than the mountain ranges that we see on land. And that whole thing is called plate tectonics. The plate meaning the continental plates, and tectonics is any kind of movement of earth or rocks, plate tectonics. And continental drift is the end result. So here in red are the margins superimposed on a globe, on a world map, by the plates. And the most famous one is the one that goes up the coast of North America, including the San Andreas Fault in California, right? And across Siberia, across the Bering Straits, well, below Alaska, into Siberia, down the coast of Korea, China, Japan, the Philippines, all that is volcanic activity, right? Volcanic region into the South Pacific, the Polynesian Islands. At a margin neighboring with the Australian plate, which is down here, keeps going down into the deep South Pacific, then across, eventually coming up again near the coast of South America. And this big one is called the Ring of Fire. You might have heard of the Ring of Fire. The Ring of Fire is all active volcanic activity and earthquakes, including the western coast of the US and the eastern coast of Asia, right? That's the Ring of Fire. It's the most well-known. It's the Pacific Plate. Then there's a North American plate that includes Alaska, Canada, US, Mexico, Central America, the Caribbean, and Greenland, which is up here, Greenland, right? Then there's a South American plate that includes mostly South American continent, an African plate, a Eurasian plate. Eurasian plate includes Europe and Asia, It's a huge one. Then there's the Indian plate. India is like a subcontinent that came from down here and crashed into Southeast Asia. There's an Antarctic plate all around the South Pole, way at the bottom, and so forth. The Arabian Peninsula is although it's a plate of its own. So now you see how the continents start making sense. The geography and the topography and the boundaries of the continents are essentially following these plate boundaries. Okay, so plate tectonics and the theory of continental drift. If we run these plates over a period of time, or geologic time, we go back only 225 million years ago. Remember, the Earth is 4.5 billion years, so 4,500 million. If we only go back 200 million of those, right, we find that there was a supercontinent. All the plates were essentially together in one supercontinent called Pangaea. Again, it's a mixture between Greek and Latin words. Pan meaning everything. Gaia is a reference to Earth, Gaia, right? The word globe somehow comes from Gaia. Geo is also a reference, comes from the Greek Earth, Gaia. So Pangaea or Pangaea was the supercontinent, a single plate that over time started cracking up and splitting and moving precisely because of the convection currents of the mantle. And about 100 million years later, a little less, about 75 million years later, we find two supercontinents. The northern one called Laurasia, which includes what is today North America, Europe, and Asia, Laurasia. And the southern plate, which was known as Gondwana or Gondwanaland, which includes South America, Africa, India, Australia, all right? This is India, by the way, for example, here. Those two main plates. The movement kept moving. The plates kept moving and separating into the continents that we know today. North America, Europe, and Asia remain together to this day. Africa by itself, South America separated, and you can see the eastern coast of South America fits into the western coast of Africa, right? India, like I say, took off from down here between Africa and Antarctica and started migrating north and eventually crashed into Asia and pushed in. That's why India is known as a subcontinent, and developed eventually the Himalayas, which is the largest mountain range of the world, is by the Indian plate pushing into Southeast Asia. All right, so it's dramatic. Australia eventually separated from Antarctica to become its own plate, and it's the smallest continent, Australia. So here's another representation of the various plates by color and name and their main movement by the black arrows. This one in particular, along the North Atlantic, along the Atlantic, it's called the Mid-Atlantic Ridge. You see, it connects 5 plates actually. There's a Eurasian plate here on the upper right, and there's a North American plate. They're diverging from each other, they're moving away from each other. So that means that this is here, this is the Mid-Atlantic Ridge. It's a spreading area where magma is coming up and moving sideways underneath the crust. This one here, the Mid-Atlantic Ridge. And it connects 5 plates, these 2 up to the north, then the African plate, South American plate, and finally the Antarctic plate down here. The long and the short is that we can come up with this geophysic map of the ocean of the world. You can see this is the Mid-Atlantic Ridge here. This is from the National Geographic. It's the physical world, not the political world, but the physical world. The wrinkles are huge mountain ridges. Here, for example, is the Himalayas, right? Here's India, the Indian subplate. Compare the Himalayas here, the largest mountain range on Earth, is nothing compared to this ridge here, and also to the bottom part of the Ring of Fire, which is here in the Pacific, because the upper part is mostly sinking in, so it's a great crevice here. In fact, the largest crevice on the oceans is known as the Marianas Trench over here. I think it's about 10 kilometers deep or something like that, the Marianas Trench in the Marianas Islands, which is part of the South Pacific. On the Atlantic is the San Juan Trench, which is off the coast of Puerto Rico. It's the deepest, it's about 5 kilometers, I think, more or less half the depth of the trench in the Pacific. And here the Mid-Atlantic Ridge, huge, huge mountain range. Okay, so that's the physical world. Then the political world looks like this, right? In other words, the almost 200 countries that we have in the world by sections. By the way, it only takes 4 colors to be able to paint all the countries of the world. With 4 different colors, you will not have 2 colors bordering each other. Okay, so on this physical world are the biomes. And the biomes are the big geographical regions, the big ecological regions. There are about a dozen biomes. There are about half a dozen on land and about half a dozen biomes on water, on the oceans. Okay, and they're called biomes because they're large ecological regions. They include several ecosystems. So doesn't matter which way we look at it, up or down, but basically the whole Earth is the biosphere. I'll show you the last slide, for example. The whole Earth, as we see it, is the biosphere. All of the animals, plants, fungi, bacteria that are living on Earth, that's known as the biosphere, okay? So the biosphere is made up of several biomes. Some biomes are land, other biomes are aquatic, mostly on the oceans. Biomes are made up of several ecosystems. Ecosystems are made up of communities. Communities are made up of populations, and populations are made up of individual species. So that's the whole hierarchy there. We'll explore that in a minute. First, a little introduction to ecology. So now we're shifting from the physical world to the biological world. All right? So ecology is all the complex interactions that occur among all the living organisms on the planet. All the relationships that occur between plants, animals, fungi, bacteria. And we're going to explore those relationships, but first we need a little bit of taxonomy or nomenclature. Some basic concepts that are meaningful and are specific to ecology. Right? All right, so let's look at the food chain, the food web, and the food pyramid. These are known as trophic levels or trophic relationship, because troph is a reference to food, right? Even to this day, the cattle goes to the trough to feed, right? Which is a huge channel where grain is put there for cattle to go feed at the trough. So trophic level is a reference to food. Autotrophs and heterotrophs, remember? The autotrophs are the ones that produce their own food. Heterotrophs are the ones who don't produce their own food, so they feed on the autotrophs. We also know them as producers and consumers. Plants are autotrophs or producers. Animals are heterotrophs or consumers. So a simple food chain with only 3 levels, 3 trophic levels, will go like this. Beginning with plants, they're the producers. Then a consumer that feeds on that producer is going to be a herbivore, because by definition, a herbivore is feeding on herbs, is feeding on plants. So the primary consumer, the first level of consumer is going to be a herbivore. And then whoever feeds on the herbivore is a carnivore, because that animal is eating another animal, it's eating meat. And so the second level of consumer will be a carnivore, in this case, the owl that feeds on the mouse that feeds on the corn, on the wheat, right? So that's a simple food chain. But we know that in nature, it's not simple, it's complicated. So it's going to be a more complicated level. First of all, there's another layer, there's several layers in between the owl and the mouse. Okay, when it's, for example, a snake that eats the mouse, and then the owl eats the snake. So you have someone in the middle, or better, let's say, an iguana. Because an iguana can eat animal, but can also eat plants. So it's called an omnivore. It's called an omnivore. It's an opportunist. Grass, they eat grass, and especially flowers. The most pretty flowers you have, they'll eat those. The iguanas, they're nasty. And we have them.
All over the place.
Yes. And they come from Central America. Okay, so that's a simple food chain, but more real in nature is a food web. And this is an example of how a food web would look like. We got the plants down here. It could be the leaf of the plant, or it could be the flower of the plant, or it could be the fruit of the plant, or the seed of the plant that a number of animals are eating, anywhere from a pica, which is kind of a South American rodent, birds, amphibians, butterflies. But it's not the butterfly itself. Is the caterpillar that eats the plant, and then the caterpillar turns into a butterfly. The butterfly will suck on the nectar of the flower, which is still kind of a herbivore in the sense that it's sucking nectar from the flower. Okay. Then squirrels, that will get into mammals. So all these, the first layer of primary consumers are all herbivores one way or another. Then the second layer is what I was mentioning, they call omnivores. And they can either feed on plant or animal, back and forth. That's the second layer. And then above that will be eventually the carnivores. And they're usually known as top carnivores. And they're usually fewer in number of species and fewer number of individuals within species. All right. And that has to do more or less with the amount of food that is required for every pound of flesh, literally, of the animal. All right. It's a pyramidal thing.
And how about the one that is underneath?
Underneath where?
In the ocean or the water?
Oh, in the water, we have similar food chains. I'll show you another example of that occurs there also. So for example, it's easier to spot the top carnivores. What are the top carnivores in the oceans? Mostly sharks and the carnivore whales, like the sperm whale and so forth. So whales, you have two categories. You have some whales that are carnivore, like orca, the killer whale. That's why it's called killer, right? And then other whales actually feed on plankton and krill, which are tiny little shrimp, right? So you have the two opposite extremes in whales, top carnivores and literally practically herbivores in spite of their huge size. But in general, the size, the larger the animal, the more top they are generally. However, for example, a deer is larger than a puma, for example, or a moose is larger than a wolf, and yet the wolf is the top carnivore, right? So there are exceptions. The same food web you have in the oceans also, for sure, and you also have in lakes and rivers, so it can be on land or water. What is generally not seen, but it's important to complete the cycle, is the saprophytes. The saprophytes is just a fancy word for decomposers. And decomposers are fungi and bacteria. And they complete the picture because sooner or later, all of these plants and animals are going to die. And if they don't rot and if they're not decomposed, then we'll be filled up to our ears and beyond with dead corpses of plants and animals. All right. And so fungi and bacteria play a crucial role in ecology, in the environment, to decompose, to fast forward, to digest that organic material, the carcass of animals and plants, down to eventually minerals that the soil, that will be in the soil for plants to reabsorb and recycle back into organic compounds. Okay. So the saprophytes, which is just a fancy word for decomposers, are crucial, but we generally don't see them. They're the fungi and the bacteria. Some fungi we see, the mushrooms, but not all fungi. Because typically these are microscopic and they're in huge quantity. In fact, we actually have two ecosystems going on. One that we see above ground and the other one that is below the soil, right? Or in the oceans. All right, so that's as far as the food web, kind of qualitatively. Quantitatively, we talk about the food pyramid. And the average ratio here is about 10 to 1. In other words, for a polar bear to put on 1 pound of flesh, it needs to eat 10 pounds of seal. Wow. 10 pounds of seal flesh, all right? For a seal to put on 1 pound of flesh, it needs to eat 10 pounds of cod or whatever other fish you're catching, and so on. The argument goes down. Every feeding level, every trophic level, right, is about a 10 time, it requires 10 times more food to feed the next trophic level, more or less, okay? Now, this can happen on land, this can happen on the oceans, and it's about the same ratio. At the very bottom of the pyramid, it's going to be what?
Well,
what is feeding all the consumers? The producers, which on Earth are going to be plants. In water, it's going to be algae and also aquatic plants. All right. And also one that is floating that is called plankton. Plankton we have, so we have plant plankton that is called phytoplankton, and then we have animal plankton that's called zooplankton. And they're microscopic, but they're there. The upper few inches of the ocean is like a like grass that is microscopic on the surface of water, mostly the oceans. And they start the food chain and the food pyramid and the food web, plankton in the oceans. On land is the plants. All right, so I mentioned that hierarchy beginning with population. So a population has a very specific meaning. It's two or more individuals of the same species. Remember, of the same species. Two or more individuals of the same species. Okay. Now, two or more populations come together to form a community. And the community with the physical factors included, that forms the ecosystem. So let's look at some examples. Here are 4 different populations of very different size and makeup. Let's start with this one up here, right? These are what? Tigers, Bengal tigers, right? From India. So how many individuals, is this a population?
Yeah.
Yes, why?
Because there are 2 or more of the same species.
Same species, all right? And in fact, there are 4, right? the mom and the 3 cubs. So that's a population of tigers, Bengal tigers. Now, here's a population of what? Penguins, emperor penguins. I've never counted them. I don't know how many. I'm going to say maybe 100 or 200. All right. But this is a population, they're emperor penguin, right? Okay. Look at the back here. You see these little black dots in the back?
Yeah.
Most likely those are what? Those are also penguin, but they're facing the other way. So we see the back side of them, which is black. All right. So they're facing the mountain. They're facing the cameraman. And so these are also penguins. And most likely they're also emperor penguins. But they are in a different area, in a different geographical area. And so this is a different population of emperor penguins than this one. It's a different population. Over time, if these 2 populations remain separate from each other, that could be the beginning of speciation, because it comes a point where these penguins, these emperor penguins over here stick together. They don't recognize the penguins from this other population. Something that maybe we don't see, but maybe they smell differently. And they're pretty smelly, you know, because they're eating fish, raw fish all day, and they're pooping around and stuff. So animals generally are pretty smelly, and they smell each other, and it's part of staying together. It's a smell. So, or the musk. So at some point, it could be that if these penguins continue to stick together and don't mix with the other penguins, at some point they will not recognize each other as penguins, as emperor penguin. And if they don't recognize each other, they won't mate with each other. They will not mate with each other. And that could be the beginning of speciation or subspecies, right? Or because there's going to be variation in between the 2 populations. So just as a side. But basically, so you understand the concept of population is a very specific one in biology, in ecology, and in the environment and environmental speak. 2 or more individuals of the same species in a particular geographical region. It happens not only with animals, but also with plants. So here is a population of pine trees. I don't know what these are, spruce, but these are pine trees. And you can see it's a whole colony, it's a whole huge population, thousands of pine trees, all of the same species covering the side of a mountain or a hill, all right? There's another population here that is not that obvious, but it's there. And it's also a producer, in other words, plant. The ground cover, right? The grass on the ground cover. There's probably several different populations because there'll be different types of grasses and herbs and weeds down here, but the scale doesn't allow us to see them. All right, so actually in this picture, there are several populations going on, but the most obvious one is the population of pine trees. What are these? At the bottom right here. These are bacteria, circular bacteria, of course, with a microscope and colorized. They're called cocci, which are circular, like a coco, like a coconut, right? They're circular. These are cocci. They're bacteria are classified by their shape into cocci or bacilli, which is a bacillus is long, or spirilli, which is a little spiral. Those are the 3 main shapes of the bacteria: cocci, bacilli, and spirilli. Right. So these are cocci. It's a colony, little colonies of bacteria that are tiny, microscopic, but they are also a population. Okay, there's 2 more individuals of the same species. All right, let's go to community. How many species do you detect here? So we got turtles, right? How many turtles?
I see 3.
3 turtles, and they all seem to be the same turtle, probably hawksbill. I think these are called hawksbill turtles. 1, 2, 3, assuming they're the same species. That's a population of turtles. Then we got fish. There's obviously 2 different types of fish here, right? These yellow and black stripes are called sergeant majors. And these, anybody know what these are called? The blue ones? They're called tangs, tang, T-A-N-G. All right, so these are purple tangs. There's also a blue tang. There's a yellow tang. So how many sergeant majors?
4.
at least 4. 1, 2, 3, 4. And this one is probably Sergeant Major over here too. Okay. Heading the camera. And how about the tanks? 2 and 3 and 4. All right. So you see, so assuming that the sergeant majors are the same species and the tanks are, the individuals are the same species and the turtles, how many populations do we have here? 3 populations, which makes a community. Not to mention the coral, because the coral looks dead and it's just the skeleton of the coral. And the algae and the microscopic stuff that is floating around, of course, which is a lot there. We don't see it, but it's there. So just from the macroscopic scale, we can see at least 3 populations. So we have a community. All right. And still just at the biological level, at the level of living species. How about ecosystem? Then the ecosystem will follow. So here we have community of populations, right? We got population of black bear, we got population of wolves, white, this is the white heron, the heron. There's a crab, the uka crab here, turtle, not the salmon, the trout, raccoon, don't miss a squirrel, and Bambi here, deer, right? So this is definitely a community. That's just the animals. Imagine the plants. We got land plants, we got water plants here, all right? So this is a community. They're all living more or less in the same geographical region, different populations, a community. But now we also want to add the abiotic factors, the non-biotic. So remember, generally the A in front of the word negates the word. Biotic is a reference to life. So all the living organisms, plants, animals, the fungi and the bacteria that we don't see that are there. But now what are the non-biotic, the non-living factors that also have an influence on the life that is occurring here? Rocks. Exactly. Rocks, the minerals, about the water itself, right? The atmosphere, the amount of oxygen that's there, the temperature, the humidity, the pressure, the atmospheric pressure, the amount of light and heat. So all these are physical and chemical conditions, factors. They're non-living by themselves, but they are part of the ecosystem. They make the ecosystem. So communities that include the abiotic factors are ecosystems. And that's the bigger picture. So that's what ecology studies. Ecology studies the ecosystem. And that's why ecologists, they're not just biologists or botanists. They also have to know a little bit about mineralogy. They also have to know a little about weather, atmospheric conditions. They have to know about hydrology, chemistry, you see, meteorology. So the ecologist is looking at the big picture, at the realistic picture, rather, of everything together.
Father.
Yes.
So I've always had kind of this question about ecosystems, of when does an ecosystem start, if you could put it that way, and stop? Because is there like a boundary? You say so many communities, and then after a region, you no longer have a continuous ecosystem. It's just a separate ecosystem, or is it just one community within? Like, I'm not 100% sure. Yeah.
Yes. Okay. So obviously the answer, is fuzzy. It's fuzzy. The boundaries are not very well delimited because you have populations wandering in and out of various ecosystems. This wolf may be hunting here now, but maybe at the top of the mountain tomorrow, hunting in snow, and that's a different ecosystem. All right, so you have the same individual or the same population moving through different ecosystems. Or you can be in the same ecosystem, but different times of the year, where there are, especially in the temperate region, where there is more weather change, and typically the 4 seasons. So it's really dynamic and fluid, and that's why we always have to talk about a particular geography and a particular weather, time of the year, and so forth, all right? So there's a certain fluidity. What generally stays most stable is the geological part of it. That's the one that stays generally most stable, but everything else flows in and out of that ecosystem, all right? And then there are categories. And that's why ecology is really, it's a cluster of other sciences that feed in. Yes, but it's a fluid system. Yeah.
And it could happen that if they, I don't know if the rivals emigrate, like leaving.
Yes.
Then the ecosystem could die too.
Exactly.
If the trees are feeding this
yes
population, but they're not coming back.
Right.
How can they?
So you hear about ecosystem collapse, right? When the change is dramatic, either on the biota or on the abiotic factors, when it's dramatic and especially fast, sudden, not in geologic time, that ecosystem can collapse. And also it's a chain reaction, because if the plants are the first ones to go, then the animals will follow because they have nothing to feed on, all right? And so, yeah, that's what we have to be, and that's what climate change is impacting, is the ecosystems, one way or another. Yeah. All right, so here is the major terrestrial biomes. There are 4 to 6 of them. So we have from the more warm regions of the world, we have either grassland, desert, or a forest, and there are different types of forests. There are basically generally like 3 types of forests. You have a tropical rainforest, otherwise known as a jungle, right? Tropical rainforest. Or you have a temperate forest in the middle range of North America and Europe and temperate Asia, where you have more or less the 4 seasons of about 3 months each. That's called temperate forest, right? And then you have the coniferous forest, which is up in near the Arctic Circle, which would be basically Canada, Siberia, that whole region there. Or you can get the same effect when you go up a mountain. Remember, we covered vertical stratification. Going up a mountain, you get similar stratification from tropical rainforest, temperate in the mid-region, and then coniferous on the top of the mountain. That occurs typically in South America, around the equator, up in the Andes, right? As you know from Colombia. All right, and then when you get very high up within the Arctic Circle, there is the tundra. And the tundra, one characteristic of the tundra is that it's so cold here, the winters are prolonged, and it's so cold that the water that is under the soil is frozen. It's frozen, and it's called permafrost. And so what happens with permafrost is that the roots of trees are not able to penetrate, because trees can go into liquid water, the roots, but they cannot go into ice because the water is not available. Water is frozen. And so you have basically no trees in the tundra. All you have is little herbs and grasses and mosses that grow on the surface, but the roots are not very deep at all. All right. And there's a little micro thawing at the level of the surface during some of the months of the year in the summer, where it's a little less cold. And so some mosses, mostly and lichens and herbs, get to grow there. And so the elk and the moose and so forth can wander in and feed periodically, seasonally, and mostly in the few short summer months. But for the rest, the ground is frozen, and so there are not bushes or no trees that can grow there. That's called the tundra. Okay, we have similar for water. In fresh water, we have 4 main ones: the lakes, where the water is mostly stable not too much motion. There is internal motion by the convection currents and other currents that occur in lakes, but it's fairly stable, the water in a basin. Then there is rivers where the water is flowing, sometimes even rapidly. So different ecosystems, right? They have to be able to attach and hold on and so forth. Otherwise, they get swept down by the current. Then you have a marsh or a swampy area, which has different conditions from the lakes. Typically, swamps and marshes don't have too much oxygen in the water. So they can even have conditions called anaerobic conditions where there's little or no oxygen. And so different type of animals and plants live in that area. The Everglades is similar to a swamp or a marsh. It's not actually a swamp, closer to a swamp. But the Everglades is between a river and a marsh, because actually the Everglades has a shallow running water on top of it, 3 to 5 inches of average, that flows on top of the coral rock of the limestone. And it's flowing very slowly, but truly through the whole ecosystem of the Everglades. So the Everglades is a unique ecosystem. And that's why it's also known as a national park, because one of the characteristics for a national park is that it's a unique ecosystem in the United States. You know, it's unique, all right? It's one of the qualifications for being named a national park. And then it received federal funding, which is from the Park Services. Finally, there's the estuary, which is where the water empties out, okay, into the ocean. And there you have the ebb and the flow of the tides. So sometimes at high tide, salt water meanders in, and at low tide, fresh water meanders out. So the animals and plants that live in the estuary have to be tolerant and resistant to both fresh and salt water, sometimes twice a day, because in the Atlantic there are two tides. In the Pacific there are 2 tides. In the Atlantic we have single tide daily. Just 2 more slides, amazingly. Going to the marine environment, there are 3 main ones. The coastal region, which is also known as littoral, L-I-T-T-O, littoral or coastline. Then there is the bottom of the ocean, which is called benthic region, the benthic region. It can be shallow or deep, all right, but it's the ocean floor. And then there's the pelagic region. The pelagic region is the water column. And you have a whole series of animals and the plankton that live all their life, basically, in the pelagic region. Except when they need to lay their eggs, they'll come to the littoral region to lay their eggs, and then they'll migrate back out to the pelagic region, which is the water column itself, all right? And they spend the rest of their lives just swimming through the oceans. So those are the 3 main ones for marine environment. When we put them together, we have the biosphere. So today we'll be talking mostly about the formation of the universe, the planetary system, and planet Earth with liquid water. And so what is called the lithosphere here, I was calling the geosphere. Litho is a reference to rock. Then going forward, we'll look at the atmosphere, and we'll look at the hydrosphere, and then we'll look at cycles in nature, etc. But that's the end of today's lecture. Okay.
Wow.
So questions, comments? We can breathe now a little bit.
For our Saturn,
Yes.
there is more about what we just did now. Not
Yeah.
necessarily the physical and physics.
Exactly. The physical is mostly background. Again, follow the scheme. You know, it's front and back, this page. Follow the outline. It's there for a reason. So I suggest just fill in with sentence or 2 for each, even in bullet form, so that this gets full. And that's the end of that. All right.
Sir.
So by Wednesday midnight, and the next is see you next Saturday.
You're gonna post the.
Yes, so I'll download this, and by this afternoon, I'll send you a link
Okay,
to the YouTube.
okay.
All right.
Thank you, Father Trophy.
Okay, my pleasure. Thank you all. Stay
Thank you,
well. Okay, thanks a
Bye.
lot. All the
Take care,
best.
Father.
Bye.
Thank you. Bye.
do we have a sentence for the class? Or-